I started recording. So thanks everyone for joining. I will share my screen. Let me know if you see it.
Yeah, it's okay.
Great. And I will start the presentation. Great. So first of all, again, welcome everyone. For whoever is new in our webinar series, or what we call a PRIZ Academy series, and whoever is not familiar with PRIZ in general, PRIZ is what we call an engineering thinking platform, but it's more than just a software platform. It's a whole methodology of tools and methods that enable the companies to generate the innovative solutions that the companies need to stay competitive and profitable. And of course, anything that we do inside the organization, especially that as an engineer, so we're solving problems on a daily basis, effectively, this is what we're getting paid for. There's no other purpose. If there's no problems, we are not needed. So this is where we're helping engineers and companies overall to overcome this process, the thinking process when we problem solve. And today, interestingly enough, we're going to talk about one of the tools. It's not our tool, it's coming from the TRIZ methodology. Officially, it's called 9 Windows. We extended it a little bit and we call it 9 Windows Thinking, because the thinking portion is the most important thing. It's not the tool, it's how you use it is the most important thing. And of course, why do we want to use this thing? In this particular scenario, what we want to explore is how do we use this tool to understand where do we need to invest today so we succeed tomorrow, do we win tomorrow? And we usually start with a quote. In this case, it's from Abraham Lincoln. The most reliable way to predict the future is to create it. So let's start. Now, let's talk about investment first, right? What is investment? And we usually start digging into a lot of available definitions. For example, Cambridge Dictionary, it's the act of putting money, efforts, or time into something to make profit or get advantage, right? So it's an act of putting money, investing the money or some sort of resources, but the only purpose of that is to get future profit and future advantage. Now, from Oxford Dictionary, very similar, but they're focusing here on investment, right? Investment itself. And the interesting part in here that they're trying to explain the investment through the process of investing. What that means that this word is not very clear and not really easy to explain what it actually is. So they're explaining through the verb of the same thing, right? But what is investing? It's not clear from here. Investopedia did a little bit better job, and it's the act of allocating resources, usually money, again, with an expectation of generating an income or profit. Again, we're allocating resources, so it's an allocation versus an investment. Interesting distinction, but it actually important distinction. But still for the whole purpose of generating income, higher income and higher profit, right? McKinsey and Company, they're saying commitment of resources. That's also an interesting differentiator, because it sounds like if it's once you decided to make that investment, you are committed to do so, and you have to go forward with it. Interesting, but it's still for the future benefit or return, so the future profit. And then there is an international financial reporting standards. Apparently, we didn't even know about this company, but it's a huge organization. And they define it in an investment is an asset acquired with an intention of generating an income, right? So you're acquiring something, you're investing into something, and acquisition could be in many different forms, of course. But again, with the purpose of generating higher income, higher dividends, and so on. Now, we have our own definition. An investment is a deliberate effort, not allocation, not commitment, not investing of money, but effort to solve a problem, how to create a value, not necessarily profit, not necessarily money, but a value, whatever the value means, not by maintaining the current system, but by transforming it. And this is where the most important piece comes from. We can invest into different technologies, into existing technologies, and maybe improve it a little bit, but that's not real investment. We're not going to gain a lot of value by little tweaks, right? So the investment is a process of solving a problem of strategic value creation. Once we solve the problem, how we create a value strategically, now we can be smart on how to invest. Now, from a formal definitions of what the investment look like or different expenses look like. So in general, there are high level two different expense types, right? There is OpEx and CapEx. So OpEx, it's an operational expense. It's something that allows us to run the business on a daily basis, make sure that it functions as it's designed to function, whether it's salaries, rent, utilities, any maintenance, anything else that we have to put the money on to make sure that the company operates as it's supposed to, as it's designed, right? From a tax perspective, this is something that is getting recognized immediately. So you spend money on salaries or rent or anything like that, it is written off from the taxes, right? From a strategic perspective, the only purpose of these expenses is to make sure that the business is running smoothly on a day-to-day basis. The other piece of it, the other type of expense is a capital expenditure or CapEx. And this is where the investment mainly is. The purpose of that is to provide the long-term value. It's acquisitions, it's buying new machinery, technology, developing new IPs. This is where the investment comes in. And by the way, we're talking about not the investment from like VCs or somebody putting money into the company where it's effectively acquiring part of the company. But when the company itself decides, okay, we need to invest in ABC, right? So it's the investment of resources within the company for future development, for future benefits. Now, interestingly enough, when we buy new machinery or new technology or anything like that, it's not one time spent and gone, it is, from a tax perspective, it is getting realized over the years, not immediately, not within the same year. For a lot of machines that we're buying or even a car, it's typically spread over 5 years, but it depends on what are we actually buying within for future. So, and then whatever we bought, it's getting depreciated over its useful lifetime, right? And again, strategically from a capital expense, it enables growth, innovation, future competitive advantage, and so on. So we're investing in ourselves to do something better, something different. So you can see strategically these two investments, they different. One is to make sure that whatever works today continues working, and another one to enable something in the future. Now, one interesting, some interesting numbers in here that if you take the CapEx and OpEx and take a ratio between them in different industries, you can see very specific industries or different industries have very specific ratios. And interestingly enough, semiconductors manufacturing is from 0.5 to 1.5 and more because of potentially heavy equipment, long technology cycles. It needs a lot of investment to be able to produce whatever they produce, to produce microchips, right? And then on the other hand, we have software, right? Something that usually runs very, very quickly. There is not a lot of research that you see from software companies. There's not a lot of equipment that coming from that needs in software companies. But usually the expense is on a day-to-day basis, which means basically people's time, right? You're buying a computer and you're hiring somebody. That's a typical software company, right? And then you have everything in between. Now, if we look at the maximum of these ratios, again, from the same industries, of course, we can dig into all kind of other industries, but semiconductors is typically anywhere around 1.6 ratio between CapEx and OpEx. This is where the innovation is. This is where the research is, a lot of research. This is where a lot of expensive equipment is, and so on. And then there's software. Like we talked about, there isn't a lot of investment. They want to move fast. They want to break things. And typically, they paying for that dearly over time. And then automotive, traditional manufacturing, and consumer electronics, anywhere between. It depends where the knowledge is coming from and how the machinery getting maintained and so on. Now, from a profit and a total cost perspective, there's few parameters that we usually look, again, at a very, very high level, right? Of course, there is a revenue. So it's a total income of sales, or whatever the income is. We talked about the OpEx and CapEx. So OpEx is fully deductible within the same year. CapEx is depreciated over time. Of course, the depreciation that we take into account when we calculate the profit. And the profit is, we're talking here about the profit before tax. We don't care about the tax at this moment. So typically the profit is calculated, again, at a very, very high level. It's a revenue minus the OpEx, minus the depreciation part of the capital expenses, right? Now, that's all great from accounting perspective, but what does it mean for the owner, right? The cost of ownership is still all of these. It's CapEx and OpEx all together, and OpEx over time. Now, it's the total cost of ownership usually calculated by the capital expenditure plus the operating expenses over time. So the sum of all of these. If you think about it, if we already determined in here that the more innovation you're doing, the higher this ratio, it means potentially you have less operational expenses. Then over time, in order to reduce the cost of ownership, right, you need to invest in the CapEx more and create the more innovation, so you can reduce the operational expenses over time. Anatoly, did I miss anything here?
Oh,
I feel like
just only one point that different companies can play with their profit, and you can affect depreciation level. And some company needs very high profit because of stock, and some company needs lower profit to pay less tax. But from the standpoint of ownership, from the standpoint of investor, this is the same, and this is what we should remember. Okay, sorry.
No, thank you. Thank you for reminding me that. Now, from a PRIZ vision approach, investment is planning a solving strategic problem, right? We talked about the fact that at the very beginning about the definitions, but if we look at it from a problem-solving perspective, the investment is solving a problem in a structured, creative, and analytical way. To make sure that the investment is not thrown away, pretty much, right? So we can actually get the most value out of the capital expenditure and reduce as much as we can from operational expenses, right? So the wise investment is coming from a proper problem solving rather than just guessing. And many times, as investors will say, we investing with a ratios, maybe 1% will succeed, right? What that means, they don't know where to invest. They don't know how to invest, and they don't have the strategy for that, and they just guessing. And that's what we mean here, guess what? And in general, even the investment itself, the act of investing, it's also an act of solving a problem of where do you invest, how do you invest, and what do you invest, right? And this is where the PRIZ platform comes in and provides the tools and methods that enable to make these rational decisions and strategic thinking, focusing on the future, on the right future, or creating the right future. And some of these tools, they already exist on the platform, or part of this methodology. It's a 9-window thinking, the one that we're gonna talk about today. There's also functional modeling or functional analysis, what we call, that allow you to identify critical functionality of the system, or where it fails and why it fails, and basically model the problem. There's a contradiction analysis that allows us to break through contradiction and understand how we solve the actual problem or the root cause that we're finding. And of course, the change flow thinking, which we released fairly recently, and that's a tool and a method that allows us to analyze the change and reduce risks and understand what the change means. And also that affects how much we invest. Now, 9 windows thinking. Let's dive into that. And what does it mean? First of all, why is it there? What this tool is? And it's an analytical tool designed to map the system across both space and time. And we'll dive that into a moment. But what does it help us to do? First of all, it helps us as well, like many other tools, understand how the system operates, but most importantly, how it evolves over time, right? We can potentially, if we understand how it evolves over time, like any other engineering system, we can potentially predict the future, right? Or understand where the direction of that particular technology or that particular system goes on. And of course, recording the changes in terms of, usually it's done in maybe documents, some Word documents or anywhere, or in somebody's head. This is actually a systematic way to document these things. Eventually, it will allow us to make much more strategic decisions about where to invest as a company. Again, not as an investor, as a company. How does it work? Right? And let's look at a very simple example. If we look at the house, right, and we look at this from one tiny hole, and all we see is a house, right? We see it's a brick house. There isn't a lot of information in that, but great, it's a house, right? We can't really say what it's made of. And this is where the subsystem comes in, or we can potentially look through another window and look at the components from which this house is built from. In this case, we can look at the bricks or windows or whatever else we want to analyze, right? Let's say it's the bricks in this point. So the subsystem in this case, it's components from which the system that we're analyzing is made of. In the same approach, we can look one level up and basically say, okay, that house must be some part of some bigger system. In this case, it's a town, right? So the house becomes a component of that town. And this is what is officially called a analysis in space, right? So this axis is called the space officially. So we're looking at the component, we're looking at what it's made of, and we're saying we know exactly what it's what system it's part of, right? So again, it's a space axis. Now we can take it further and we can say, how did it look in the past, right? And we know the past. That's not very hard. And we say, okay, in the past, it potentially was a wooden house. It was made out of timber. Timber was a subsystem of that wooden house. And yeah, it wasn't a town. It was a smaller village, some smaller community, in this case, a village. And if you think about it, we now start analyzing the time. So we're already seeing the space and time axes where we're analyzing one simple thing, in this case, just a house. But we can take it further, right? We can start thinking in terms of what future is going to look like. So in a subsystem level, we can say it's timber, brick, next is concrete blocks, right? What we already seen today. Village, it became bigger, it became town, now it became city. Great. But in order to build a city, we need bigger buildings. Now it's kind of natural that it will go, it will be built out of concrete buildings and so on, right? So again, we analyzing from just one house, we can extrapolate it into how does it look like from a space perspective and from a time perspective. Now, in this particular case, we know about the concrete buildings and cities and concrete blocks. It's all good as an example. And typically how the 9 windows analysis, thinking analysis works, it's a simple matrix like we see here, where in the middle, we have the current system that we interested in analyzing. We need to understand what's the subsystem. So basically it's component, supersystem, which system that our house is part of. We doing the same for past because we will know that. And we're trying to understand what is it going to look like in the future. Now, what does it mean look like in the future? Every line from a time axis perspective, it needs to have a logic, right? It needs to have a progression logic or evolution logic. And let's look at a couple of examples. Digital image, right? We all know what digital image is. Let's dive into that. So digital image, what we take on the phones, image is stored as digits, right? So we can say it's some sort of virtual particles or particles in quotes on a physical storage because eventually it is saved on some sort of hard disk. Now, what's a super system of that? Where this digital image is used? It could be PowerPoints, could be digital albums, it could be many other things where we're using the images, right? Now, what about the past? The past, we know the analog what is called
Film.
Photo images.
Film. Thank you.
Photo images.
Thank you.
Yeah.
So it's an analog image. It's basically a chemistry. It's a image stored as particles, right? So we can say it's a physical particles on physical storage, right? And of course, we had photo albums, physical photo albums. Many people still have them today. I have one here. Amazing. Now, what about the future? If you think about it, and that's what I was what I was talking about, a logical progression, a logical evolution, right? We're seeing physical particles on physical storage, virtual particles on physical storage. Well, logically, we can say it's the next step should be virtual particles on virtual storage. Now, what virtual storage is, that's a different story, but that's not a hard disk. Hard disk or even a cloud, which eventually going to be in a hard disk, it's still a physical storage. Now, from a super system perspective, we had photo albums, we have some digital photo albums, some digital media where these images stored, but it's still on a physical storage, right? And then next step must be digital album on that interesting virtual storage. But what does it mean? Like what can be constructed here in the middle? And what we say, it's a virtual image on a virtual storage. But what is it virtual storage again is, right? Virtual storage could be potentially a biosystem. Now, biosystem, it's a little bit weird, right? It's still technology, still something physical. But if you think about it, we can potentially remember the image, right? You don't have to open an album and see the image. You can remember the image. What does it mean? We're not sure, but that's the direction. Now, of course, there is a problem of how do we share the image? And this is where the interesting part begins. Because once we learn how to share the image between us without any additional device and still see the same thing, the same experience, that's going to be an interesting development. Let's see another example, cell phones, right? Cell phones today, it's some sort of physical device that's coming with us all the time. It's in our pocket, right? The base component for that whole thing to exist, to even make sense, we need to have a person who holds that phone and the phone itself. And that whole thing is a part of a bigger system, which is network of antennas with servers, with any other devices that are allowing that communication, right? Now, in the past, we had wired phones, but what wired phone means, it actually tied to a wall. So it means that the person had to go to the phone to use it. Okay, interesting. So the components here, we can say it's a person, phone, and wires as a base components that allowing the system to even function. In kind of similar scenario, it's a network of now electric wires that used to be in the past with phone stations and you name it. Now, logical progression, if we had person, phone, and wires, and then person and phone, logically, we should be left only with a human being. What does it mean? We'll see in a moment. Now, at the very high level, at the super system level, it's a network of people, potentially with antennas and servers, but maybe not. But the most important, it's a network of people. The only conclusion that we can come up, it's a person basically becomes the phone, right? And antennas receive the sound from the person. That sounds surreal, but if you think about it, the phones today, they literally, we need to hold the phone, the device that converts our sound waves into a digital signal that getting transmitted over the air to antennas, which transmitted to the other side, and then the process reversed to make the sound on the other end. Great, but
Sorry
technology
for,
already, yeah.
It seems to me that the phone comes instead of the person.
That's a philosophical question, but yes.
Our entity becomes the phone.
Right, but maybe not we need to become the phone, but the phone need to become us, right? And here we're talking specifically about how do we communicate. Of course, the phone today is far more than just a communication device, right? It's a computer and everything.
Because in the past, we were communicating directly, one with the other.
Right.
So are we going to go back to this situation, but overcome the distance and the other limitations that we had in the past?
That's a perfect question and answer together, I would say. Because think about it. The only thing that, like you said, the phone allows us to do is to communicate a sound, our own voice or whatever, to the other side of the world, potentially, right? Now, if we overcome this gap or this problem of how do we communicate it, then we don't potentially need the phone. Now, the interesting part that the technology already exists, right? There's a lot of military devices that or spying devices that you can pick up a sound from a very far distance very effectively today. Now, is it developed enough to be used all over the place? No, but the same as GPS, it wasn't developed enough many years ago, and it was only used by military. So what, right? Today, it's available on each and every one of us phones.
I wonder how we can use this tool for the idea of what Nikola Tesla vision was with electrical circle which has no wires I'm sure you are well familiar with the vision.
Right. Mm-hmm. I mean, listen, there's additional concept that probably worth mentioning that this is actually coming from TRIZ method, TRIZ theory, right? Where all systems they developed uneven, right? So every system will have different components that have development and different levels. So one system is usually developed less, and this is one that we're trying to invest in typically. Now, if you think about it, usually one of these lines already kind of in the future, right? So you already potentially have a technology, or you at least have an idea of what are you going to do with that technology, where are you going to progress it. But something in the middle, in this case, the phone, how the phone is going to look like based on what we already know in a subsystem, and a super system, we can potentially extrapolate that and envision, like you mentioned about Tesla, he had a vision and envision how is it going to look like in the future, or how it potentially can look like in the future. And that means we know potentially where to invest in, right? But all we wanted to say, it might sound crazy, and all these analysis sounds like a dream, but the technology exists, and this pattern repeats all the time. Whether we're going to use it, that's a different question. But we can, right? So these things, they're a true potential for investment for the future. How much to invest? We don't know yet. That's the next question. Anatoly, you want to take this one?
Yeah, let's talk a little bit about metallurgy, about tantalum niobium. I spent a long time on tantalum niobium chemistry and technology, but it's very, very typical situation in metallurgy when we should separate material from impurities and also separate from a neighboring component. Like tantalum niobium, they are very they have very similar chemical properties, therefore not very easy to separate them. And there are a lot of other pairs like tungsten and moly, titanium and zirconium, and so on. So tantalum and niobium today is separated by liquid extraction. You don't need to be PhD in chemistry. I explain it in a few words. Just it's two immiscible liquids mixed, and after that separated, and one metal is coming into one liquid and another one remains into another liquid. So the subsystem liquid and liquid. And super system is a mixer settler system, very similar. We should mix two immiscible liquids, and after that to settle it, to make them to get separated. What do we have before? We have fractional precipitation. When we dissolve everything, dissolve or concentrate, we have both tantalum and niobium in the solution. Now we add something to precipitate salt containing tantalum. By that way, that niobium will remain in the solution. What do we have in the subsystem? We have liquid plus solid. And the super system was just huge reactor for precipitation and separation filters. Nothing more than that. Now have a look on subsystem, liquid, solid, solid, liquid plus liquid. And the next step, I'm so sorry, nothing to say, only liquid and gas. So the next step of technology in metallurgy will be, Alex, show please. is decomposition with plasma. So the system will be plasma decomposition. This is the future of technology. Plasma is everywhere. It's interesting. Plasma came to us from analytical chemistry, ICP plasma method, but it becomes a very strong method in manufacturing, for instance, in semiconductors and microchip manufacturing everywhere. Let's have a look. Let's think what will be after the plasma. What is the future? So let's pick up system in present is a plasma, is a process in microelectronics. The subsystem is, we studied it in primary school, radicals and ions. So, and super system is a plasma flow. Okay, and what was before? You know, before we used furnaces, we pick up wafers and placed it into the furnaces. And what does it mean, furnace? What do we have in a furnace? We have hot gases. And hot gases, what hot gases is? Molecules. Now, let's have a look. Molecules, radicals, ions. The next step logically in the future, electrons. Maybe small ions, but small charged parts. Now, let's have a look what oven means. As I said, we place wafer into furnace and we heat it it's volumetric heating. This is 3D heating. Plasma flow, plasma heats and treats only surface. This is 2D heating. What we will have in the future? 1D heating, lines and points. This is electron jet. And believe me, the future of semiconductors and microchip processing will be electron beam processing. Without lithography, very expensive lithography, no, lithography will exist inside of a computer. So let's go to the next step. So Alex, you can continue.
Yeah, thanks for that, Anatoly. So just in these, last 20 minutes, maybe, we did very simple analysis, very quick analysis, and we already have basically 4 different directions of where potentially we as humanity, if you will, can invest, right? We looked at the virtual memory and what does that mean and how that potentially might look like. We had an acoustic wave instead of the phones, right? The plasma processing and metallurgy. And of course, the electron beam that we just uncovered for microelectronics. And I will pause here if you guys have any question. If not, I want to switch to the platform and show another case that we have in the past. One of the times we worked with a small startup. They were working on their product and they were trying to understand what's the, by the way, this is how the 9 windows thinking looks like inside the platform. And I'll expand a little bit more in a second. But they were looking at what to implement and how potentially their product can look like in the future to solve a particular problem. And after about half an hour or maybe an hour of analysis with them together, they came to the conclusion that whatever they're building is not needed at all. So they're basically wasting time on building the whole solution, this whole startup. And interestingly enough, they didn't have any clients, they didn't have any traction at all, and I think they invested about 1.5 years into building this product. That's another example where, yes, it's where to invest, but it's also where not to invest, right? Now, on top of that, what we have here, once we understood where to invest, that's not the end of it. That's just the beginning, right? Because once you understood, okay, let's invest in a phone without a phone, what does it mean? It means you have a whole bunch of different problems that you need to solve on the way. And these problems require additional tools and methods that will help us to do so, right? Today we have 12 of them. Each and every tool is built for a particular purpose, and we call them descriptive, diagnostic, and prescriptive tools. Descriptive are the ones that, of course, it's understand the system and the problem that we're working on, the problem space, what's officially called. Diagnostic is the one to help us analyze the problem and diagnose the problem. What is it we're going to solve, or where the root cause? That's typical diagnostic tools. And of course, prescriptive. Prescriptive are the ones are the tools that helping us to come up with the solutions or ideas, or both, and quote unquote prescribe the solution going forward, right? And when you're working on these additional investments and trying to solve these problems, it's not a single problem. It's a series of problems until we get to the end, and even after. And just a reminder, we want to make the investment as efficient as possible, so our operational expenses the smallest, as small as possible, right? And all of these tools and all of these methodologies. So tools is just a tool, of course, but the methodology itself helps us to do all of that. And I'll pause here if you guys have any questions. We're actually ahead of time.
Are these tools software tools?
Yes, these are software tools. All of these software tools, it's a cloud platform. I'll switch to another workspace. It's a cloud platform that allows us to use all of these tools as an individual, as a team, and it's basically documenting the entire thought process, as well as, if you need to look at what was the solution and why was the solution made a particular way, in a year from now, 5 years from now, 50 years from now, it's all available here, right? And if you think about it on an organizational level, it also allows, enables continuous learning as well.
Alex, maybe we have some small time. You can show, for instance, cause and effect chain and functional modeling, just to show how it
Right.
looks like. Yeah.
Right. Let's go into functional modeling. This is also from microelectronics, one of the real projects from the past. Again, in this particular case, and by the way, in any step of the way, we're we're encouraging people to write down as much as they know, as much as they can, right? And document as much as they can, because that's also part of the thinking process, and there is no way around it. Otherwise, all the knowledge becomes proprietary to that person who knows about it. Once we have that description, we do the actual modeling itself, right? And the functional model in particular can look something like this, where every system, it has a product. So every system is built to add value to the product or create a product. A system consists of multiple different components that have their own functions and their own purpose. And then there's different type of component, which is a super systems in this case, that exist, it affect the system, but we not necessarily can affect them, right? What we do as a result, this is something that a human being needs to build, right? It's not something that machine can potentially build. The machine can a little bit help, maybe, and we're exploring these options. But the human being eventually needs to build. And as part of building that, first of all, what we do, it helps us to understand how our own system works. And it's amazing how often we see that people think they know how system works. They don't know anything. They know just a little bit of course.
Can I can I ask a question? Does
Oh.
that software have the ability to auto arrange things?
What do you mean by
you know
auto
what I-
arrange?
Well, like let's say you add 5 nodes between the orange element and the closest white one. You have to add 5 elements because you forgot to add them. And its lines all start to cross and get messy. Does it have the ability to automatically clean things up?
I mean, currently we didn't implement it automatically, but you're free to move things around as much as you
Yeah,
can.
you can.
That's
Okay,
not a problem.
got
Right.
it. That answers. Yeah, that
Yeah.
answers my question. Thank you.
Yeah, but technically it's doable.
Yeah, I
There's
understand. Yep.
different options for that. So as I mentioned, first of all, it helps us to understand how the system works, from a function terminology. And what we typically see a lot of times is people do draw diagrams and diagrams of components, but these diagrams usually describe the interaction between components, but not necessarily the function, right? And that's a very important piece. The function of what defines basically why the component is even in there. What's the point of having? But once we have the model, we can run a bunch of different calculations, and specifically functional rank and problematic rank. And these ranks will allow us to understand if there are some components that don't have any value, or they create a bunch of problems, right? These are the ones that we want to get rid of going forward, or potentially where the problem is coming from. And of course, the functional rank. So it serves a lot of different purposes, right? So speaking of a future investment, we can imagine or design any system that we want, but usually what happens, or typically what happens, people will create a proof of concept, some simulations. So spend a lot of money and resources to understand, will it even work, or how is it going to look like? What this allows us to do, it allows us to model our future and potentially see, does it even make sense? Of course, it's not 100% answer, but it will give us much more understanding than not having it at all. Is that right? So the way that we many times see how the system is used, the functional model, we can simulate the change on a particular system and see how it will behave going forward, right? That's another tool to potentially look into the future as well. Now, of course, there is additional calculation as well, and there is comparison between different versions of these changes. So for example, this one, we reduced the component, we removed the component and replaced its function with something else, and so on. So it's a very flexible tool that allows to analyze anything without actually implementing anything, right? And of course, another tool with more diagnostic is cause and effect chain, kind of the same concept. We trying to encourage people to write down as much as they can, especially about the part that they want to analyze. And then typical cause and effect chain might look like something like this, right? With all the tooling around it and color coding for easier documentation and easier manipulation. And that's a discussion point as well. And this whole system is built for one purpose and one purpose only, to generate ideas, right? And eventually all of these ideas, they're getting collected in the idea manager. And idea manager will have additional tooling to help us to understand which idea we're taking further, which one we drop, or maybe different concepts. So we're providing the tools to analyze, to help people analyze the ideas in the list. And of course, finally, we want to generate the actual solution, right? And solution is not necessarily a single idea. It might be potentially multiple ideas combined together. But this is a documentation piece where we as engineers, or as a group of engineers, or any group, in fact, will document as a proposal, here's the solution going forward. In this particular case, we have a short-term and long-term solution. One is, kind of a mitigation approach, and another one a long-term redesign of the system. And of course, a report. Report is an interesting piece. It's something that engineers typically hate doing. We worked that hard. We found a solution. Now we need to report on it. Nobody wants to do that. So this is done automatically because we have all the information. We have the entire thought process of the group who worked on it. So again, who was the group? What was the background? The original problem where we started from, the problem statement, which we're also providing the tools to help with. Winning ideas. So which ideas did we actually use to provide the solution and the proposed solution? But we're not stopping there. We have all the tools that we ever used in this project inside the report as well, because that is effectively the thought process that the team took to come up with a solution, right? And again, talking about the documentation, especially in regulated industries, this is very important. That's a document, so it can be used for document control or anywhere else. This is the solution, this is the reasoning, this is what we implemented, and the entire track record of that, right? So that's a fingerprint of your team's solution, if you will. I'll pause here.
Yeah, I would add. Yeah, I would add just a few 2 words that it's not trivial platform. It requests knowledge, and we have very good developed onboarding process, including lectures, including coaching and help with project start, beginning and moving. So
happy to answer any questions.